All right, 10:50 exactly. So we are still on track. Yeah, so hopefully you're all refreshed, had some coffee, had some snacks, and we're ready to go for the next session. Our next speaker is Filippo Bisotti. Filippo is with SINTEF, and he'll be discussing the Bio4Fuels project and how they've used CAPE-OPEN in their project. So please, Filippo, take it away.
Thank you very much for this kind of presentation and also for the invitation to this event. Okay, so this is the outlines for my presentation. So I will introduce a little bit why we need CAPE-OPEN tools essentially for the modeling of bioprocesses, in this case, the biorefineries. And I will present you the case study, which is the Bio4Fuels project. And finally, some conclusions and also some overview and overlook of our activities using CAPE-OPEN tools in SINTEF industry. So why do we need to rethink about bioprocess modeling? Because now currently the flow sheet simulators for, I mean, just to put in Aspen Plus, Aspen analysis, and you need to design pyrolysis, gasification, biomass pretreatment. These tools are too simplified because sometimes, quite often you need to define yield and that's all. So essentially, if we have a process and we are feeding something from experimental data, we can tune the model and know what it is the output of this pyrolysis process. But what happens if we change the feed and the operation and the operating conditions? We don't know because we need models. So essentially, we need a rigorous model to design this type of equipment because the systems are extremely complex. And also we needed to properly design and sizing the unit. And our motto is make it is as simple as possible, but not simpler, if we wanted to quote Albert Einstein. So essentially what we want is, I'm changing the operating condition, but I'm still able to understand what is the output condition. So for sure it will be different because I'm changing the feedstock, but I'm able to understand what it is happening inside my system, and I need a rigorous modeling. Our strategy is essentially based on data. So essentially we started from experimental data and we generate sub-models. These sub-models are plugins we insert inside our flow sheet. And after that, we can do all the techno-economic assessment we want of the process. This is the loop that we need to think about when you need to design or to, in any case, model bioprocesses. So the need is, I wanted to design, size, upscaling, and also have a preliminary assessment of the cost and the carbon mitigation of my process. So I need a model, but the model is based or need to account for complex and huge variability of my feedstock and my operating conditions. So I need a rigorous model for a conventional system. There is a constraint. The system accounts for thousands and thousands of molecules, but I cannot manage thousands and thousands of molecules in my process simulator. So I need a good predictability with a reasonable computational time. So the solution is to lump the molecules, to reduce the number of molecules that I will have to handle in my simulation flow sheet, and after that to my module and my sub-models in order to match the experimental data and understand what it is happening inside my system. And also we want to be transparent in what we are doing. So essentially the data should be open, the models are available in the literature and are tuned or in alternative are tuned for a specific application, but we are able to report it, to report our models, and the techno-economical is completely transparent. So essentially we are using literature model to estimate the cost, and in this way the numbers are not coming from random selection of numbers from a box, but essentially there is a transparent procedure how we make it, and also the RCA is trackable, because sometimes you read some papers in the literature and you say, okay, this is not completely transparent. I don't understand where the number are coming from. So Kyle asked me to report a little bit on Bio4Fuels, and Bio4Fuels will be the case study to present our procedure using CAPE-OPEN tools. The Bio4Fuels is a project founded by the Norwegian Research Council for close to 13 million. And the scope was to develop new technologies to speed up also the development and the deployment of biofuels and biotechnologies. And also involved many other R&D institutes, but also industrial partners in these projects. And that's why it is important also to have a cooperation between academia, research, and industrial entities. I put on the top right corner the QR code, so at any time you can have a look at our webpage with more details. The strategy for and the objectives for Bio4Fuels, essentially the scope of the work was we start from the biomass. We want to split in a very effective way cellulose, hemicellulose, and lignin, because the post-processing of these different parts of the biomass are completely different. So I need to be efficient and effective in cutting the biomass into these components. And cellulose and hemicellulose are converted to a fermentation process to get bioethanol, and then the biomethanol is purified until fuel grade. On the other hand, the lignin is a waste, but we recover it as through pyrolysis a bio crude oil, and then finally biofuels. So if we start from the scheme that I proposed before, essentially we have to start from the data. The data are coming from our colleagues, and to do that, So the strategy is we need to separate the different cuts, increase the sugar yield, and valorize the waste carbon. But to do that, we need data, which means measurement, and details, which means molecules and chemistry. To do that, we started from this publication within the project from our partners, Aniko, Vincent, and Roman. And they propose a lab scale process, and then we needed to adapt it. For the species, we have quite exotic molecules, and so we identified the potential missing data. For sure, there are no data for some molecules. And from hundreds of thousands of molecules, because at the NMBU, they identified the molecules, we said, we are not able to manage 2,000 molecules. We needed to change our approach. We needed to cut, identify what are the most important molecules inside the system, and then we needed to define the properties. The properties can come from the NIST database or can be estimated, but at the end of the day, we needed to define the properties of the molecules, and for the molecules that are not defaulting the database for cocoa, coffee, or whatever you want, we needed to define a PCD manager. So we are preparing a tab, and we are storing the molecule inside of the PCD manager. This is an example. So if you start from the cellulose, you need to identify what is the unit for this polymer, so the glucose. For the hemicellulose, you need to identify the C5 sugars. And then you have some strange guys to define the lignin. There is a lignin rich in carbon, in oxygen, in nitrogen. For sure, these molecules are not present as real in nature, so you need to define the properties using GANI methods and so forth. And then you prepare the tab in PCD and in PCD manager, and then you use in your simulation. And then if you have a look also to the pyrolysis bio crude oil, there are thousands of molecules. There are models suggesting some molecules, but you can easily understand that these molecules are not present in the default database. So as before, you define the properties, you estimate the properties, and then you use the estimated properties in the simulation. Then we need to account for the sub-models. So essentially, we started from the process that Aniko and colleagues identified. We remove the lab scale steps because, of course, for instance, when you need a buffer solution to control the pH, I think that's the side is not possible. You just put soda if you need to reduce the pH. You just put a strong acid if you need to reduce if you have to go below 7 pH 7. So essentially, we identified a structure of the process, and after that, we completed it with missing steps that are possible, feasible on an industrial scale. This is the flow sheet, and we used COFFEE version 3.6 and CAMSEP 8.4 for the separation. So essentially, the process started from the pretreated biomass. We have a steam explosion, but I go through it because now I'm presenting you with some models. We are using 3 different kind of sub-models, rigorous and detailed models. So essentially based on literature model that, for instance, to describe the pyrolysis, we have the kinetics, we have the identification of the main steps, the reaction mechanism. Data-driven models, whenever you need to tune your model based on your own experimental data, we identify the data-driven model and then we put it into Cocoa Coffee. And for other models, for instance, if larger facilities are already existing, for instance, the fermentation, we are using the NREL data. So essentially is a yield black box. We know what is the production, what is the yield of the process, and then we put into Cocoa Coffee. So essentially, the rigorous model is used for the steam explosion, for the rectification of the bioethanol, the allotropic distillation. So to break the allotrope and then get pure bioethanol, the pyrolysis, the HDO, the distillation, and also for the steam generation. Here it is an example. For instance, we started from Ramsey model to characterize the pyrolysis of cellulose and hemicellulose. For the lignin, we adapted the Lussan model. From that one, we tuned the model in order to understand what is the optimal temperature window in order to achieve essentially a good conversion of your biomass and to increase also the bio-oil yield of the process. And if you're interested, we published it at the Escape 33 in Athens. That is the publication over there. But I think you will get the presentation, so I also put the link. Data-driven, for the enzymatic saccharification, the system is quite complex, and also the LMPO is an activated enzyme to handle the enzymatic saccharification, but there are not so much data on the literature. So we used the data that Aniko got on the lab scale, and essentially we define the yield of a process based on 3 different parameters, which are the initial yield, H, which is a step function, and the kinetic, pseudo-kinetic constant of the system. And these parameters are essentially function of the steam explosion temperature, which is the step before the enzymatic saccharification, and also the concentration of the enzymes. So we regressed this coefficient to get a proper understanding of the system. And finally, we got something like that. And also this one is published at the Escape 33, so you can get or you can retrieve the model there. And as I mentioned, for the fermentation, we used a black box model. So essentially, we relied on the NREL report on the fermentation, which is quite detailed. So essentially, we are able to predict according to the feedstock, so the sugar-rich hydrolysate, what is the yield of the process and the production. Now we have all the sub-blocks, and we can put everything in a flow sheet, and we simulate everything using COFFEE. And this is published in a conference proceeding from the last Escape 34 in Florence. This is the process. This is the basic process. So essentially, Now we have the flow sheet, but we can improve it. Why? Because we can optimize, we can have energy integration, we can intensify because, for instance, there are some cuts that can be used for the biomass pretreatment. So essentially, we don't need additional external consumables to improve the process. And also we can valorize waste and low value it. So we started from the simplified process, and we got the fully integrated flow sheet. I'm sorry, but probably the green shaded rectangle, I don't remind you if you see, but for instance, we have the enzyme production on site to reduce the cost for to purchase the enzyme for the enzymatic saccharification. We are producing in situ the steam for the steam explosion, and also we are able to generate the heat for the pyrolysis. In this way, we are going to consume one of the products, which is the biochar, but at least we are able to supply the heat for the pyrolysis. And also this is reported in the second proceeding at the CAPE-OPEN. Now we have anything in place because essentially we have some models, we have a flow sheet, we have optimized, we have energy integration, we have anything in place. But now we need also to think about, is this process profitable? Is this process carbon negative? We need to think about this because we can speak about anything, but money are running the world. And then you need also to be carbon negative or at least carbon neutral. Otherwise, your fuel is like a conventional fuel. So now we are ready for the techno-economical assessment, and I will show you the iterative procedure that in SINTEF, my subdivision likes or loves to use in any project. So essentially, we start from the simulation. From the simulation, we get the stream table and the unit operation, and from that one, we are able to provide or estimate the techno-economical assessment. So essentially, we are able to estimate the capital and the operational expenditures, the cost for all the supply chain, and in this case, for instance, we also accounted for the impact of the hydrogen quality. So in HDO, which is the bio-crude oil hydrogenation to remove benzenes, double bonds in the molecules, you need hydrogen, and we calculated the techno-economic assessment according to the different quality of hydrogen, gray, blue, and green. And then from the techno-economic assessment, you are able to estimate the selling price to be competitive with the fossil fuels. So essentially, which is the correct cost that I can cover all my expenditure to produce my biofuels, and I wanted to know how much I'm competitive against, or essentially what is the gap with the conventional fossil fuels. From this step, we are able to understand where we need to put more efforts to reduce the cost of the production of my biofuels. On the other side, we need also the LCA because we need to understand what is the environmental impact of my process, also according to the hydrogen quality that I'm using. I need to address the carbon neutrality of my process, but also for the full supply chain. And for this step, my colleagues at NTNU used the Brightway, which is an open source Python-based LCA program. And finally, the output is we can identify which are the most carbon intensive steps of my biorefinery. So from that one, we can retune so essentially from the input from the techno-economic assessment and the LCA, we can retune or rethink about the design of a biorefinery, get new data, new flow sheets, new stream tables, and then reassess the techno-economic aspects and the life cycle aspects. So this is an iterative loop between people working on modeling, people working on techno-economic assessment, and people working on LCA. And as I mentioned before, we need transparency. So we are using something that is fully reported and anyone can retrieve and can recalculate. And the key point is always, is the carbon reduction feasible? Because I can suggest to change the process from the LCA perspective, but then I need to understand, is this economically appealing? Because this is the point. And we are going to present this at the GHGT 17. And essentially, finally, we guess, can it be the biorefinery carbon negative? Yes. And how it is possible? We are producing a little bit of carbon. Carbon as a CO2, but if you capture the CO2, we are carbon negative. And we used our in-house software tool for the CO2 capture. We account for two different blends, two different amounts actually. One is the Caesar one, which is expected to replace the MEA. And we got the different to be optimized the CO2 capture, and finally we got that we are able to be carbon negative, and also this will be presented at the GHGT 17 in a couple of weeks. That's all for Bio4Fuels, but I'm pleased to say that in our division in SINTEF industry, we are CAPE-OPEN and coffee friendly. So essentially, these are the projects where we are using CAPE-OPEN tool, and specifically coffee, in hydrogen production, like in yield, in co-feeding of pyrolysis oil with VGO for steam crackers to get syngas, as in Revolution, or valorization of biomass waste, like in Valuable, biomethane production, like in Sempre Bio, production of safe aviation fuel, sustainable aviation fuel in Fuel Up, in electrochemical processes, like in Loxichem, or in the production of green ammonia as hydrogen carrier in hydrogeny. And then there is also formic acid production in Iconic. The project will be started up as soon as possible. We are also open to disseminate our activities. So these are the congresses where we presented something on the CAPE-OPEN tools and their potential. And I would like to thank all my colleagues. I know that Olaf is online, and yeah, we are a small team, but we have many projects, and we found out that the CAPE-OPEN tools are very useful for our purposes, not only to save money, but also because there is a huge flexibility, and we can do what we want actually with CAPE-OPEN tools. Thank you very much. And if you have any question, I'm happy to take any comments also during the lunch break.
Any questions for Filippo? There's one question online.
I need to ask.
Question online from no, has the hand gone away? Maybe got one short question while we wait. So you mentioned that there was this iterative process where you've got your flow sheets, you then got this link to Excel, and you've got this LCA link. Is this iterative process automated in any way, or is it still a very manual method?
It is not automated because essentially we want to because we need different tools, and the purpose is completely different, because from the idea is to integrate everything, but it is quite difficult because we want to have step-by-step full control of what it is happening. So from the technical assessment, we wanted to have the Visual Basic result, the flow, the Excel spreadsheet result to see where is the bug or the problem of the process, and the same for the LCA. If we are going to integrate everything, it is quite difficult to debug or to see what is actually the problem of your process.
But I understand you're pulling the data out of your streams using unit operations that log the data for you.
Yes.
We have a better machinery for that. It's called flow sheet monitoring. That's one component that has access to all streams, rather than you having to put all kinds of.
Yeah, we generate from that one the stream tables, and then we share with people for the technical assessment. From coffee, we can do anything. We can extract probably also the coffee.
All right, I see we've got Ala with a question.
Yeah, thank you very much for the talk. Actually, there are two questions online. So one question was from Vladimir. He asked, what NIST database did you use? What NIST database did you use when you referred to it on one of your slides? And another question was from me about, have you tried using high-level quantum chemical calculation instead of group contribution method, because it's well known to give more reliable results for some properties like enthalpies of formation, heat capacities.
We use the GANI for that purpose, which is a contribution method. And
but there are
Yeah.
also, I can send you a link to an article from one of my colleagues who developed a high-level quantum chemical calculations with really reliable results, if there are no experimental data.
Okay, I'm happy to get it. And what is the first question?
What NIST database are you referring to when you on one of your slides?
NIST database. We have access to the NIST database. We have the program to interface the famous RefProp, and from that one you can get the information on the molecules. And
RefProp. So you mentioned RefProp, right?
Yeah, there is the RefProp, and you can extract the data over there.
Okay, thank you.
And in case there are also publications, but if you have a look also to NIST web book, there are directly links to the publication with the experimental data, so you can retrieve also the data there. But
Okay,
obviously, only for conventional molecules. If you need to work with levoglucosan, you need the estimation method.
Actually, there is an experimental work from on heat capacity for some of such materials. Okay, so I'm not taking more of your time. Thank you.
I think we have one more question from Harry. Harry? Harry, you there? You have a question? All right. No? Oh, is the okay? He says you're typed, and I think we will get to your question after. We can't hear you. Sorry about that. CO2 negative.
Only if you capture. No, because there are two reasons. Because we are carbon negative, we are using green hydrogen from electrolyzer fully run with renewable energy. Fortunately, in Norway we can do that. And on the other side, we are capturing the CO2 at 95 or 98%, I don't remember. And we can store it. So essentially, we are recovering the CO2 from the carbon. And plus, you have the biochar. The biochar is also a carbon negative process because it's carbon stored as solid.
I was just wondering, you said that you are doing actually the lumping, right? And what details are you going to lump? Are you using more components and
we are using directive variances model. We are using a directive variances model, which is based on cellulose, hemicellulose, and lignin. The lignin is defined as Lic-Chi, Lic-H, and Go. From the distribution of the atoms, so carbon, hydrogen, and oxygen, and also the ultimate analysis of your biomass, you know how much cellulose and hemicellulose is present, and that's fine. From that one, then you can estimate the distribution of the building blocks identified by Ranzi for the lignin, and then you use this kinetic model using lumpy molecules. So essentially, lumped system. So essentially, Ranzi uses like 30 molecules at the end to identify the different. So you have hydrogen, CO, CO2. blah, 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 and then levoglucosan, the strange guys that I showed to you. So, senapaldehyde, coniferyl alcohols, the formic acid. Formic acid is not strange, but you need the different aldehydes, ketones, and so forth. Ethanol, methanol.
Thanks.
I think we can thank.
No, so sorry.
Oh,
And we are not we are not lumping models from by our own. Okay, so essentially we are retrieving models from the literature, because otherwise it's too time consuming. Also because the time horizon for the project is 2-3 years. If you need to delamp and then validate a model, also for different feedstock, it is just 3 or 4 years of activity.
So we find that in the paper.
Yeah, I retrieved from the literature.
let's